Hello and welcome to this technical presentation series on renewable energy studies. In this series, I will show you how to model PV and wind for load flow simulation, harmonic analysis, and in EMT programs in general. Of course, I will use EMTP for that. I will also present you the renewable energy toolbox in EMTP and present some typical integration studies that must be done and that can be done with EMTP. As an introduction, and I guess everyone watching this video is aware of that, with the increasing penetration of renewable energy like solar park and large-scale wind parks comes many challenges. Those challenges have been forcing TSO to modify their grid connection requirements, and new requirements came out like reactive power support, frequency support, low voltage ride-through, which are called LVRT, high voltage ride-through, HVRT or OVRT. Also now in some country, and it will probably be generalized in the future, some requirement on negative sequence contribution for all these inverter-based devices, which are the wind parks and PV parks. Of course, with that came new challenges to operate the grid, but also simulation challenges, which has to be solved by a software company like EMTP. So the first operating challenges are, of course, the power availability, as sun and wind are not available at all time, but the loads need power at all time. So here there is a challenge to face. Network stability is also a big challenge, as those inverter-based devices have a completely different dynamic compared to the synchronous generator. Power quality is also a challenge, as inverter-based devices inject harmonics in the grid that must be filtered to have a good power quality. Flickering can also be a problem. The short circuit behavior of these components are completely different compared to, again, synchronous generators. Resonance issues can occur, what we call subsynchronous control interaction, when the interaction between different wind parks and solar parks and the grid can cause resonances. Protection settings are also different and must be modified compared to traditional approach with synchronous generator. And finally, we have islanding detection problems when the parks are operating. In terms of simulations, to be able to simulate and study wind parks and solar parks precisely, new models have to be developed, and now I can say have been developed because it's done. And of course, there's more work to do to improve generics model and manufacturer models, but I think now we are getting to a very good place. The model have to be precise, the simulation software have to get more precise. The industry is slowly shifting to use more and more EMT-type software in order to simulate precisely those renewable energy integration. We have to be able to simulate nonlinear models and very, very large grids in EMT-type software. So if you take the example of EMTP, an integration study can look like that, at least a simulation design. Here, this is an example taken in Quebec from Hydro-Quebec. It's in the Gaspésie region where you have most of the renewable energy integrated there. It's kind of far from loads and dams. So you see here we have many wind parks, many manufacturers in fact, and so we're able to simulate that in EMTP pretty well. In fact, this circuit is not that big, but it starts to be a bit challenging to simulate. Of course, with EMTP, we can simulate much bigger design. We are now really specialized in simulation of large grids. I think the largest grid we've simulated is like several 100,000 buses. So all that we can do it. Also, simulating something like that is made possible because of the load flow, which is embedded in EMTP, and our initialization techniques, where we initialize time domain simulation with load flow. I will come back to that later in the video and in other videos, but just as an introduction, those are like pretty important things to look at to simulate renewable energy integration. So what is it? A solar or wind park model? It's something like this. We have here the point of common coupling connected to the transmission network. Then we have typically a park transformer, so wind park, solar park transformer. a park controller which will send the individual voltage or power reference to each inverter in order to respect the power and reactive power the park is supposed to inject into the grid. And so then we have different collectors where you have here all the PV arrays and their inverter connected. Each of them has a step-up transformer, which we can see in very small, and here the pi section in between are the cables or lines connecting each inverter. Of course, this is a very big representation of it, very challenging in terms of simulation. You can imagine if we simulate a grid scale network with any time there is a park, we model all the inverters, that will be very, very challenging to simulate. However, for some studies, we have to go through that. We have to simulate the full detailed model, especially when you study temporary overvoltage inside a park. So when you have a single phase to ground fault inside the park here, we will show example in another video. When you do harmonic analysis, it's also important to model that in detail, especially for Windpark. The collector grid can have a frequency response and can, of course, amplify or filter some harmonics. When you simulate fault in general or events occurring inside the park, of course, the park must be simulated in detail. To validate the aggregated model, we will discuss aggregation of this model after, but in order to aggregate, first we need to validate that the aggregation is correct. For that, we can compare the results. To do precise LVRT and OVRT study, low voltage right through, over voltage right through, it is also important to test with the detailed model and then generalize with the aggregated model. And of course, finally, to study the energization of the park, where each feeder are energized one after the other. In this case, the problem is, the inrush current you will find in energizing each transformers that can create a voltage drop. Of course, you need to model the park in detail for this. So I was talking about LVRT and OVRT. Obviously, when you have an under or an over voltage at the grid level, because the collector grid is spread out geographically, you might not have the same voltage seen by each inverter. Here we see a difference between an aggregated model and the full detail model and what each inverter sees during an under voltage event. And so of course you can see that some might trip and some might not because the voltage is not the same. So how do we aggregate? Well, you have here some techniques. Most of the aggregation is based on the power flow. So you have like several inverters which are represented here in parallel, and each of them has a connected impedance. So based on the power injected by each, which is represented by N1, N2, and N3, you will create an equivalent here where the equivalent impedance is calculated like this, basically through the power going through the impedance. And then if you have like several feeders in parallel, so first you will do the equivalent like this for each feeder, and then an equivalent for the different feeders. And so it's the same concept. Based on the power through each feeders, you will create an equivalent impedance. So the only thing you need to know to do that is the impedance of each cables or lines and the power going through. So then it looks like this. So this is the EMTP model. So this is an aggregated model. You have again the point of common coupling here, the park controller, the park transformer, then maybe grounding, capacitor banks for reactive power control. And starting from this point, the model is completely aggregated. So here this is the collector grid equivalent, where we just explained how to calculate the impedance. Then you have here the converter transformer, which is aggregated. The aggregation for a transformer is pretty straightforward. Simply change the power base in order to rescale the converter transformer according to the number of converter. And then here you have the actual converter aggregated. I will discuss after what are the other components here. For now, we can disregard them. So one of the big advantages of EMTP is that within the same software, we can run load flow simulation, steady state simulation, time domain simulation, and so on. But obviously, we need a model which adapts to the type of simulation. And that's what the model that we have in our renewable energy library does. The first type of simulation, which is the most common, it's load flow simulation. The goal of the load flow simulation is you have a certain value of wind or irradiance. If you're at, early in the day, at noon, late in the day, and you want to know what power your wind park and solar park can inject, and what is the overall power flow on in your network. The model that we use in this case is fairly simple. The park will be modeled as a PQ constraint. The power generated will be determined, like I said, by the wind and the irradiance, and the reactive power will depend on the control mode. If the park is operating in Q mode, then the reactive power will be the Q setting. If it's operating in droop or in a PV mode, we will have other constraints that represent PV or droop modes. The load flow model in the end, it's after we'll visit the actual model in EMTP, but it's inside this little box here, model for load flow solution. We actually also use this block to initialize the converter. Converter initialization is something pretty difficult. Yes, after the load flow, what is the voltage and the angle at this bus, but to initialize completely the converter, it's a challenge as the control is non-linear, so it's hard to find the states of each variable just based on the voltage. That's why we need to find techniques in order to initialize the converter without creating a grid perturbation. The worst case is to have no initialization, and when you start the time domain simulation, all the PVs and wind start from a zero power and ramp their power to the nominal. This is a very bad case, because imagine if you have a high penetration of renewable, your network will lose stability during the simulation, and you will have to wait a very long time in order to simulate an event if the simulation ever goes to stability at some point. Instead, in EMTP, we use a little trick. What we do is, after the load flow simulation is run, we retrieve here the voltage and angle found during the load flow, and inside this block we have this ideal voltage source, and we will force this ideal voltage source to the same value found during the load flow. So when we start the time domain simulation, this ideal voltage source will be connected here, and from the grid perspective, the park will be an ideal voltage source which injects the good power and reactive power. While we have this ideal voltage source connected, the converter will also be connected and will be able to ramp its power up. That will take something like 0.2 or 0.3 seconds. As soon as the park injects the nominal power and reactive power, basically all the power will come from this branch and nothing will come from this ideal voltage source anymore, so we will disconnect it. And from the grid perspective, the only difference is at some point the power is generated by the ideal voltage source, but then it's injected by the converter, so it might have some harmonics in there, but the power flow will be the same and there will be no large disturbance in the power grid. So it looks like that. Imagine you have a small network like this and a PV park. We run the load flow simulation. We find here in EMTP the voltage, the angle, and etc. And now if we run a time domain simulation, we see that there is a perfect initialization. For the grid, it's completely invisible. Here at the beginning, this is the ideal voltage source, and at this point, this is now the converter. The ideal voltage source is disconnected. And so we can start simulating events at 0.5 or 0.6 seconds. Okay, so we discussed the load flow simulations. The next one here is about harmonic studies. For harmonics, there is a lot of debate still today in the industry on what's the best model to use and etc. So right now, where we all converge is to do harmonic studies, to use a harmonic current source with a harmonic impedance. It can also be a harmonic Thevenin equivalent with an impedance, so it's fairly the same. So based on measurements from the turbine manufacturer, you will have here a list of all the harmonics, the angles of the harmonics and so on, in relation to the fundamental. Some manufacturers may also give you impedances versus frequency. Here in this case, we don't have them, so we put very large numbers. So basically this branch becomes an open circuit. The big challenge here is that when you have all these wind turbines or PV connected through the feeder, you need to know what is the fundamental frequency injected and what is the angle. In EMTP, we solve the challenge again with the load flow. Each of these wind turbines during the load flow will be a PV or a PQ bus, like I explained. Thanks to the load flow solution, we will find the voltage at each point, but also the current. current, the magnitude, and angle. And so then when we do the harmonic study, the park will become the harmonic source through a transformer. But as you can see, the magnitude here of current and angle will be retrieved automatically. And so the harmonic source representing each converter will basically inject the current aligned with the load flow solution. And the magnitude will also be adjusted with the load flow solution. We will do a special videos only for harmonic studies later on. Here it's the example of the DFIG model in EMTP. So DFIG, doubly-fed induction generator. We have very similar to the PV. The point of common coupling is here. Then we have the park controller, which monitor the power and reactive power. This park controller will send a reference to the inverter controller. Again, all these parts is aggregated. So which means that, for example, if we have a park with 45 inverter, we will aggregate all that in one big inverter, which generates 45 the power of 1. And of course, all the impedances, resistance and inductance will be 45 times smaller. The capacitance will be 45 times bigger. So all the aggregation process is dealt with automatically by the EMTP model. We have the load flow here model and initialization connected there. We have the park transformer, the grounding if needed, same thing, a capacitor bank if needed. Obviously, you can modify this model and connect a STATCOM, for example, if there is a STATCOM or something else. Then you have the aggregated collector grid and the model of DFIG. So the DFIG, I assume everyone is familiar with the model. You have an asynchronous machine which is connected to a converter with two sides, the rotor side converter and the grid side converter. Here you have the controller. We will discuss all that in a future video. The controller of the converter, and then you have the wind turbine. In the wind turbine, we have the multi-mass model built and also the aerodynamic model of the turbine built. That again, we will discuss that. The wind is an input of the model. The wind can be changed. You can simulate gust, can simulate no wind, and full wind. So all that can be adjusted during the simulation. Same thing for the reactive power control. This can be modified during the simulation. As we will see a bit later, I will open EMTP and show you when we switch the simulation type, we will basically include and exclude some devices. For example, if I want to run a harmonic study, automatically this source here will be included and all the rest here will be excluded. I will show you that later on. I will first go to the other type of wind turbine, the full converter. The full converter is very similar to the PV. For the beginning, it's exactly the same as the DFIG. The only difference is after the turbine itself. So for a full converter, like the name says, all the power goes through the converter. So we have the grid side converter here, the DC bus, then the machine side converter, a permanent magnet synchronous machine, and the same type of turbines as the DFIG. The converter model is also here. We will discuss it in more detail later on in another video. To finish, here you have the solar park model. Only difference compared to the full converter is that we don't have the machine side converter. We directly have the PV connected to the DC bus. It's possible to have a DC boost here to adjust the DC voltage between the PV and the turbine DC bus. And again, I repeat, the control here will be explained in another video. So let's see all that in EMTP. So here you have the content of the renewable energy library. So when you have this library, it's over there. So you see you have the DFIG Windpark, the DFIG wind turbine, which is very similar to the Windpark, but you don't have a PPC model and the Windpark transformer. Same thing for full converter. You have the input impedance, which is the device over here. This input impedance is used for subsynchronous control interaction studies. We will do a video on that later on. You have the PV park, so very similar as for wind, and also a single phase PV for residential and distribution level studies. Let's quickly open an example. To finish this video, I will show you how the model adapts with the type of simulation. So when you have this toolbox here, you have a section called Renewables. And let's, for example, open the PV example here. Okay, so here if I unzoom, so you can see here the small network, so simply like an ideal voltage source with an impedance, so basically a network equivalent, then a small transmission circuit with some loads, and the model is here. If I go inside this PV model, okay, we find what I've been showing you so far. So right now the model is set up for time domain simulation. You can see because the converter is in there. Now if I switch the type of simulation, I go to simulation option, and for example I want to do a harmonic study. So I can check here frequency scan for my harmonic study. If I click on OK, you see that this part got excluded and now this one is there. Okay, if I do a load flow study, not much will change in the end. This part will stay. This part stays as well, but because of this breaker will open for the load flow, it will not be considered. So you see that you don't have to think too much. You change the type of simulation, the model adapts. Here I'm showing you what's inside, but from a user perspective, you will simply use this device, and when you double click on this device, we will go through that later, but you have a mask here. That is the interface for the user. So thank you very much for watching this video. I hope it was useful. Please take a look at the following videos of this series, where we will go more in depth into control modeling and the different simulations and studies that must be done. Thanks, and have a good day. Bye.